Hello, good evening all. My name is Ranjan Bora and I'm one of the TA in this course, Biomechanics of Joints and Orthopedic Implants. And this course is instructed by Professor Sanjay Gupta from IIT Kharagpur. And I have been taking tutorials every week from the starting of this course. And today is the last week tutorial. In today's tutorial, first I will solve the assignment from week 7, and after that, I will explain some concepts related to this week, and I will solve some numerical problems. Also, I will give software demonstration using the in the OpenSim software. So I will start now. So first, I will solve the assignment from week 7. So this was the first question from last week's assignment. This question is dash is the process by which osteogenesis is induced. So osteogenesis means the formation of bone. So the answer for this question is osteoinduction. First option is correct. Next question is which of the following statements is false? So three statements are given. So one of these statements is false. So it is talking about the bone remodeling. So first we will see what is the bone remodeling, or how many types of bone remodeling are there. So there are two types of bone remodeling. One is the internal remodeling, in which there is change in bone apparent density, and one is the external remodeling, in which there is change in bone shape or geometry. Geometry means cortical thickness. So from the options, we can see the first option is internal remodeling results in changes in external bone geometry. So this option is not correct because internal remodeling relates to change in the bone apparent density. So first statement is false. So coming to the next question, which is external bone remodeling results in change in. So we have just seen it in the previous slide. External bone remodeling results in change in cortical bone thickness. Option B is correct. Also, mathematically, you can see from this equation, dm by dt equal to rho multiplied by a into dx by dt, where m is the bone mass, rho is the apparent density, a is the surface area of bone, and x is the thickness, means dimensions in the direction of cortical thickness. So this term dx by dt, this represents the change in periosteal geometry or the cortical thickness. So option B is correct. Next question is bone resorption is due to the activity of dash cells. So bone resorption, again in the remodeling phase, there are two types of. You can see one is apposition, bone apposition, which means the formation of bone or gain of bone, and one is the bone resorption, in which there is loss of bone. So, and this bone resorption is due to the activity of osteoclast cells, and bone apposition is due to the activity of osteoblast cells. So in this case, option B is correct. Next question is D dash after total hip replacement is more pronounced at the dash part of the femur. So for this question, we have to refer to one slide from the lecture content, in which we can see there is this study by Mathai et al. In 2021. In this study, they have simulated the bone remodeling predictions and they found that we can see this color map which represented bone density. So yellow colors means 0 bone density in gram per centimeter cube, and as the color intensity increases, means color becomes more darker, means there is more bone formation. Means so that's why the bone density is also getting increased with the increase in the color intensity. So we can see here E is the section here distal part, and A, this part is proximal. This is proximal and this is distal. So we can say at this section A, we can see these color maps represent that there is very less bone formation. So that means there is not a bone gain. There is the loss of bones in this area, in this section A, that which means the bone resorption, and it is in the proximal part of the femur. So option A is correct. Bone resorption is more pronounced at the proximal part of the femur. Okay, here in the distal part, we can see bone apposition is more pronounced. Next question is, the reference stimulus for bone adaptation is obtained from. So here there are some equations for bone remodeling. That means the rate of change of bone mass is relates to this stimulus. This S underscore ref means this is the reference stimulus, and the S, capital S, it is the remodeling signal. And so the reference stimulus for bone adaptation is obtained from, so this reference stimulus S underscore rep, we obtain it from intact Taffy model. That's why this stimulus is used as a reference. Next question is, dash is proportional to the difference in remodeling and reference stimulus. So we have seen the equations for bone remodeling. Here are the equations. The rate of change of bone mass, this dm by dt, this is proportional to the difference in remodeling and reference stimulus. So here option D is correct, rate of bone loss or gain. Okay. Next question is, among the following, free surface area per unit volume of bone is highest for. So here we can see one chart of which relates to surface area density of bone with the density. Surface area density means surface area per unit volume, and this is the mass density, gram per centimeter cube. So we can see as the density increases, then surface area density also getting increased. Then at one point, at the density value of around 1.1, it attains the maximum. This surface area density is maximum at this point. So, and this density represents the density of cancellous bone, which is 1.1 gram per centimeter cube. So the surface area density is highest for this cancellous bone of density 1.1 gram per centimeter cube. So option C is correct. Okay, next question is, shortening the stem length in resurfacing implants reduces strain shielding around the proximal femoral neck. We have to tell either this statement is true or false. Again, there is one chart in the slides in which we can see like the here two two plots are there. One is for long stem in the black color and one is for short stem in the red color. So we can see that the normalized peak strain is highest for means is higher for this long stem compared to the short stem. So that means this shortening the stem length results in reduction of strain shielding. This reduction of maximum peak strain means there is reduction in strain shielding. So this is a true statement. Shortening the stem length in resurfacing implants reduces strain shielding around the proximal femoral neck. Okay. Coming to the next question. The ability of biomaterials to be incompatible with the contacting blood is known as. So here there is three terms are given: biocompatibility, hemocompatibility, and cytocompatibility. So we'll see what these terms represent. It's one by one. So hemocompatibility means it can be defined as an in vitro assessment of the blood compatibility of any material surface and their leached out components to change the clotting factors. So we have seen that it represents the blood compatibility of any material surface. The next is biocompatibility. It refers to the ability of a biomaterial to perform its desired function with respect to a medical therapy without eliciting any undesirable local or systematic effects in the recipient or beneficiary of that therapy, but generating the most appropriate beneficial cellular or tissue response in that specific situation. And cytocompatibility, what is it represents? Cytocompatibility can also be defined as the ability of biomaterials to be in contact with proliferating cells without producing an adverse effect in vitro. So from these three definitions, we can see this hemocompatibility. It hemocompatibility means the ability of biomaterials to be incompatible with the contacting blood. Okay, so option B is correct. Next question is the direct anchorage of an implant by the formation of bony tissue around the implant at implant bone interface is known as. So the direct anchorage of an implant by the formation of bony tissue around the implant at implant bone interface is known as osseointegration. Option C is correct. Osseointegration is this stable anchorage of an implant achieved by direct bone to implant contact. Next question is the implant materials of tests such as copper, silver, and bone cement. So the implant materials, these materials, copper, silver, and bone cement, these are the type of low biocompatibility and they show less osteoconduction. So option A is correct. Because their biocompatibility is low, that's why they show very less or no osteoconduction. And what is osteoconduction? Osteoconduction means that bone grows on a surface. An osteoconductive surface is one that permits bone growth on its surface or down into pores, channels, or pipes. And they are implant materials of low biocompatibility, so little or no osteoconduction. Next question is carbon fiber reinforced peak composites have a dash due to relatively hydrophobic surface which has cell adhesion. So carbon fiber reinforced peak composites have a low surface energy due to relatively hydrophobic surface. Hydrophobic means uh, they are resistant to water. They don't react with water. Hydrophobic. That's why they limit cell adhesion. So option C is correct. And next question is trabecular orientation in bone was found to coincide with the direction of. So here we can see a bone, cross-section of a bone, and here the studies of Julius Wolff suggested that the trabecular orientation may coincide with the direction of principal stresses. So option A is correct. Next question is the functional group consists of the trabecular orientation originating from the lateral femur shaft upwards across the neck and ending in the femoral head. So these are the functional groups which we can see around in the femur bone. So here this question tells about originating from the lateral femur shaft upwards across the neck and ending in the femoral head. From this figure, we can see this functional group number 2. It originates from the lateral femur shaft and travels across the neck and ends in the femoral head. So 2 is the primary tension group. So here option C is correct, primary tension group. Next question is the hip resurfacing surgical technique causes less bone remodeling in femur than total hip replacement. So here we can see two types of implants uh, which are used in the femur. This one is the hip resurfacing surgical technique, and this one is the total hip replacement. So, and this study shows that the bone remodeling in the hip resurfacing surgical technique is less compared to the bone remodeling in the total hip replacement. So this statement is true. Because here we can see these red colors. This represents the bone density. So bone density means these are the bone remodeling results. So in this case, this bone remodeling is greater than the bone remodeling in the first case, which is the hip resurfacing surgical technique. Next question is the anisotropy of bone depends on the So anisotropy of bone, because of the presence of different functional groups in the bone, this anisotropy property arises because of this different functional group, this their mechanical behavior is different. So, and this whole groups, they results in a results in the uh, anisotropic nature of bone. So, because they are, and depends on the this trabecular orientation. Because the orientation of different groups is different, so that's why this, because of different orientation, their behavior is also different. So that's why this bone is anisotropic in nature. Next question, does the adaptation rate affect the final configuration of bone remodeling pattern? So we can see that changes in adaptation rate do not influence the final configuration of bone remodeling pattern. It only influences the time step of bone remodeling. So option B is correct. No. Next question is, what is dead zone? So from this bone remodeling chart, we can see that one is the bone apposition, which means the gaining of bone, and one is the resorption, which means the loss of bone. And there is one zone which is known as dead zone. What is this dead zone? Here, bone does not react to small deviations in mechanical stimulus. This minimal threshold of inhibitory signal required for triggering bone remodeling was later incorporated in the theory as the dead zone or lazy zone. So in this zone, the bone does not react with small deviations in mechanical stimulus. So this equation is the strain energy strain energy rate for different activities in the bone remodeling process. So here option A is correct. Dead zone is minimal threshold of remodeling signal in order to trigger bone adaptation. Next question, in multi-objective optimization problem, the S is defined as a set of non-inferior solutions in the objective space defining a boundary beyond which none of the objectives can be improved without sacrificing at least one of the other objectives. So in multi-objective optimization problem, Pareto optimal solution is defined as a set of non-inferior solutions in the objective space defining a boundary beyond which none of the objectives can be improved without sacrificing at least one of the other objectives. Option B is correct. So now I will explain some concepts from previous weeks. Then I'll solve some numerical problems related to those concepts. So one concept was this musculoskeletal model. So what is a musculoskeletal model? A musculoskeletal model means it represents the whole skeleton of the human being or any joint, uh, whole skeleton with the muscles, joints, and the bones. So it consists of three basic parts. One is rigid bodies, which is the geometry of bodies, and we assign the inertial properties of these rigid bodies, which are mass, center of mass, moment of inertia. And these rigid bodies are connected by ideal joints. Here, for example, here there is the knee joint. You can see in this figure that this is the knee joint which connects the femur with the tibia, and there is this musculoskeletal model is moved by actuators, which are muscle line of action and muscle properties. These are the parameters to define an actuator, and these are the parameters to define ideal joints. These muscles are here. These red colored one line element. These are the muscles or actuators. Okay, next there is in dynamics method for musculoskeletal modeling. So what is this inverse dynamics method? Using this inverse dynamics method, we can estimate the joint force and moments from 3D data. If we have this anthropometric data, then the marker position data from motion capture system, and the ground reaction force data. If we have these three data for a musculoskeletal model, then using the inverse dynamics method, we can estimate the joint force and moments. Anthropometric data means segment mass, length, and moments of inertia. And this from this marker position data from motion capture system, we know this velocities and accelerations. And from the force platform, we know this ground reaction force. And using the equations of motion, which are summation F equal to 0 for a system in equilibrium, and summation M equal to 0. Using these equations, we know this, we can estimate the joint force and moments. So in the inverse dynamics, there is one link segment model in which we represent an anatomical model using the links. Each bone is represented using one link. Here, this foot is represented using link 3, and tibia is represented using link 2, and femur is represented using link 1. And next, these links are separated at means things are separated at the joints in which they are connected. So here we can see at the ankle joint, these two links are separated. Foot is separated from the tibia, and from the foot, if we know this ground reaction force which is acting on the foot, then we can estimate these reaction forces at the ankle joint, RY3, RX3, and the moment also M3. So this reaction forces data we can then use for this link, for this tibia link, to estimate the reaction force at the knee joint and the reaction moment at the knee joint. Then this reaction data can be used to estimate the reaction moments and forces at the hip joint. Likewise, it is an inverse approach. So we start from the foot, then tibia, then femur, then we can estimate the reaction forces at the hip joint. So now I will solve one problem using this concept. Like first, I will estimate the reaction force at the ankle joint from this problem. Then in the next problem, I will use this reaction force and reaction moments at the ankle joint to estimate the reaction force and moments at in the knee joint. So this is the first problem. This is given for a subject in late stance during push-off. The following foot accelerations were recorded. X is given 4.25 meter per second square. AY is 2.75 meter per second square, and alpha is minus 57.35 radian per second square. The mass of the foot is 1.2 kg, and the moment of inertia is 0.015 kg meter square. Calculate the muscle moments and reaction forces at the ankle joint. So we can see here these coordinates are given. This is the coordinates for the ankle joint. And this is the coordinate for the center of mass of the foot. And this is the coordinate of the toe. So from this coordinate data, we need to first find out the distances. Distances from the ankle joint, because we'll need these distances while calculating the moments about the ankle joint. So this distance is, these coordinates are given in centimeter. This is 7.6 and this distance is 15.1. Also, we'll need this distance. This distance is, sorry, sorry, this I have taken the this should be 5.6, not the 7.6. One second. It is not working. Okay, so I will write here. This is this is 5.6. This is 11.2. And this vertical distance from the ankle joint is 15.1. Okay, this centimeter. So first we'll find out the reaction forces FAX and FAY. So mass of the foot is given 1.2 kg and the moment of inertia is given 0.015 kg meter squared. So first we'll use this equation, summation Fx equal to m ax. Here some of the forces which are acting in the x direction, F x plus Fx is 160.25. First I'll write Fx. Here are two forces which are acting in the x direction. One is this Fax, and one is the Fx. So 12 to mass is 1.2 into Ax is 4.25. Okay, from here Fax is 1.2 into 4.25 minus 160.25 equal to minus 155.15 Newton. We have found out the reaction force, x component of the reaction force in the x direction. Now we'll find out the y component of the reaction force using this summation Fy equal to m a y. In the y direction, this Fay, it is acting in the vertically upward. That's why I've written it plus. Then plus Fy and the weight of the foot, which is minus 1.12. It is given G, which means 9.8 to M. M is 1.2 into AY. AY is given 2.75. So from this equation, Fay equal to 1.2 into 2.75 plus 1.12 into 9.8 minus Fy. Fy is 765.96. So if we do this calculation, then it will come 51.6 Newton. So these are coming as negative. Fx is negative and Fy is also negative. That means here the direction, we can see this direction of Fx and direction of Fy. These are towards the positive direction of x-axis and positive direction of y-axis. And from our calculations, we have found out negative. That means the actual direction will be in the reverse direction. That's why that means Fay will be actual Fay direction will be in the vertically downward, and actual Fax direction will be in the negative x direction. Okay, so we have found out the reaction forces Fx and Fay. Now we need to find out the reaction moment Ma. So we'll take the moment equilibrium above the ankle joint. Here summation M equal to summation M equal to I alpha. Okay, I is given 0.015 and alpha is given minus 57.35. Summation M is about the ankle joint. Here we'll take the anti-clockwise direction as positive. So we can see MA is already in anti-clockwise direction, so it will be plus MA. And moment due to the weight of the foot 1.12 G, it is in the clockwise direction, and so it will be minus 1.12 into 9.8 into distance is 5.6. It is in centimeter, so we need to convert it into meter. 0.056 and moment due to this force Fx. It is in anti-clockwise direction, so it will be positive plus Fx is 160.25 multiplied by the moment term, which is 15.1, but it is in centimeters, so we need to write 1.151. And the moment because of this force Fy, it is also in the anti-clockwise direction. This Fy, it is also in the anti-clockwise direction, so it will also be plus Fy is 765.96 multiplied by the moment term is 11.2, which will be 0.112 equal to I alpha. I is 0.015 multiplied by alpha is minus 57.35. So now we need to solve this equation. Should be MA equal to minus 0.015 divided by 57.35. These all terms will take towards the right side. So it will be plus 1.12, 9.8, 0.056. Next term will become minus 160.25 multiplied by 0.151. Next term will become minus 765.96 multiplied by 0.112. So if we solve this, we will get it will become minus 110.23. Okay, this moment, unit of this moment will be Newton meter. We have taken all the units in the SI unit. So this moment is also coming as negatives. That means here the moment was in this figure, the moment was given in the anti-clockwise direction. So, but we are getting the moment as a negative value. So the actual direction of moment will be in the clockwise direction. Moment will be in this direction. Okay, so we have found out the reaction force and reaction moments at the ankle joint. So now there is this problem 2, which is about for the same instant of time, calculate the muscle moments and reaction forces at the knee joint. The leg segment was 43.5 centimeter long. Mass of the leg segment is 3.72 kg. Radius of gyration is 0.131 meter. Okay, it is the ankle joint. And it is the knee joint. So for the ankle joint, what are the reaction forces and moments we found out? So here Rx1, first we need to write Rx1, Ry1 and M1. Rx1 is in the last problem. Rx1 is this is minus 155.15. Okay, so now we need to see what it's the when we do the problem for the knee joint. So here fx direction is in the negative x direction. Okay. In the negative x direction. So here in this problem, this Rx1 direction will be in this direction, positive Rx1 direction, and value of Rx1 will be 155.15. And RY1, here FAY was in the negative y direction. So in the knee joint problem, it will be in the positive y direction, and its value will be 751.68. 751.68 Newton. And the M1, MA is also negative, and it is here, it is clockwise. So in the knee joint problem, it will be in the anti-clockwise. M1 will be 110.23 Newton meter. So we'll use this reaction force values to find out the reaction force and muscle moments at the knee joint. So here in this problem, you can see the acceleration values are given in the problem figure itself. This is the angular acceleration, and this acceleration is minus 0.3 meter per second square in the x direction and minus 4.21 meter per second square in the y direction. So again, we'll use the force equations, which is summation fx equal to m ax. From this equation, here you see Rx1 is acting in the positive x direction. So Rx1 plus in the x direction, this one more force at the knee joint, which is Rx2. Rx2, and there is no other force in the x direction equal to m. Mass of the leg segment is 3.72. Acceleration in the x direction is minus 0.3. From here, Rx1 is 155.15 plus Rx2 minus 3.72 into 3. From here, Rx2 equal to minus 3.72 minus 155.15, which will be minus 156.27 Newton. So Rx2 is also, we are getting negative value, so that means this direction of Rx2 will be negative x direction. So next we'll use the next equation, which is summation Fy equal to MAy. And what are the forces acting in the y direction? Ry1, it is acting in the positive direction. So Ry1 plus Ry2, and weight 3.72 Z, which is acting in the negative y direction, minus 3.72 multiplied by 9.8 equal to mass is 3.72. Acceleration in the y direction is minus 4.21 meter per second square, minus 4.21, and value of Ry1 is 751.68 plus Ry2 minus 3.72 From this ry2 will be minus 3.72, 4.21 minus 751.68. Solving this, minus 730. So ry2 is also, we are getting negative. That means this ry2 will act in the negative y direction. Now we need to find out the reaction moment. Reaction moment, which is m2. So here in this problem, we can see that the moment of inertia is not given. So we need to first calculate the moment of inertia. So here the mass of the leg segment and radius of gyration is given 0.131. Okay, so moment of inertia I is mass multiplied by radius of gyration whole square. So it will be, mass is given 3.72 into 0.131 whole square equal to 0.0638. Its unit will be kg meter square. So we have found out the moment of inertia for this leg segment. Now we need to find out the moment of inertia of this leg segment about the knee joint. So we need to apply the parallel axis theorem, which will be I about knee joint will be equal to I about CG plus M multiplied by this distance. We need to find out this distance. So from this triangle, we can see this is 14.2 and this is given 12.9. So we can apply the Pythagoras theorem, or we can write this as O and this as C. OC is square root of 12.9 square plus 14.2 square will be 19.18 centimeter. So here it will be I about CG plus M into 19.18. We have to write it in meters, so dividing it by 100, square. I about CZ is 0.0638 plus 3.72 into 0.1918 whole square equal to 0.2 kg meter square. So we have found out the moment of inertia about the knee joint. So now we need to apply the moment equilibrium equation. This okay, I will add one more slide here. Not getting the option. Okay. I did not sign it. Let's sign it first. So I have lost all the calculations. Okay, so I need to do it again. Or since I have already shown you the steps, I will directly do that step. Is second. So here, what was this? This distance. This is O. This is C. Then OC was square root 14.2 square plus 12.9 square, which is 19.18. So moment of inertia about the knee joint was I about the knee joint was I about CZ plus 3.72 multiplied by 0.192 square. It is ICZ was 0.0638 plus 3.72.192 square. It is 0.0638 plus 3.74 square. It was 0.2 kg meter square. Now we need to use the moment equilibrium equation, which is summation m equal to I alpha. This m, we are taking moment equilibrium about the knee joint. So, and in this case, we are assuming this clockwise direction is positive. Okay, so here, since here m1 direction of m1 with respect to knee joint, it is direction of m1 with respect to knee joint, it is in clockwise direction, so it will be plus m1. And m2, this direction is in anti-clockwise direction, it is minus m2. Next, rx1. Rx1 was in this direction. Okay. And ry1 was in this direction. So okay, let me do it. That was rx1. Rx1 was 155.15. Newton. Ry1 was 750.9 Newton. And m1 was 26.9 Newton meter. And these directions were here in this problem. We found these directions were in these directions. So in the knee joint problem, these directions are in the positive x direction, positive y direction, and in the anti-clockwise direction. Okay, so let me check the direction for a moment again. So direction of moment again with respect to knee joint, I am taking clockwise as positive. So here m1 it is coming in about the knee joint. It is in the anti-clockwise direction, so it will be minus. And m2 it is also in it is also in anti-clockwise direction m2, so it is negative. And because of the force rx1 and this distance is 12.9 plus 16.9, which will be 29.8 centimeter. And this distance is 18.5 plus 14.2, which will be 7.2, 32.7. Okay, so because of the force Rx1, its direction is in the anti-clockwise, so it will be minus Rx1 dot 0.298, 0.298, and the direction of the moment because of the force Ry1, it will be in the clockwise direction, so it will be plus Ry1 dot 0.327, and the action of the moment because of the weight 3.7 to z, it will be in the anti-clockwise direction. It will be in minus 3.72 into 9.8, and this distance is 14.2, so it will be 0.142. This will be equal to I alpha. Now we need to find out M2, moment M2. So I will take the M2 towards the right hand side. Minus M1. M1 is 126.9. And minus Rx1 is 155.15 into 0.298 plus Ry1 is 750.9, 0.327 minus 3.72 into 9.8, 0.142 minus I alpha. I is 0.2 into alpha. Here alpha is given 36.9 radian per second square. So 36.9. Okay, now we will calculate it. 126. Minus M2 is coming 59.85 Newton meter. It is coming clockwise direction because here we have the direction is positive. So in the problem, the initial assumed direction of M2 was in the anti-clockwise. So these directions will be opposite. Rx2, what was Rx2? We got both Rx2 and Ry2 negative. So the directions of Rx2, Ry2, and M2 will be opposite to what we have assumed initially. So these were the problems. Okay, now now I'll show how we can estimate the joint reaction force and muscle forces using the OpenSim software. So OpenSim is an open source software for biomechanical analysis for musculoskeletal modeling. And using OpenSim, we can estimate the joint reaction force and muscle forces for different activities performed by the musculoskeletal model. If we have those three data, one was the anthropometric data, one was the kinematic data, and one was the ground reaction force data. So using the anthropometric data, we do the scaling, which is the first step. So in the scaling, here it is performed based on a combination of measured distances between XYZ marker locations and manually specified scale factors. So here we measure distance between these markers, which are placed on some bone landmarks, as you can see from this musculoskeletal model here. These dots represent the markers. So these are the virtual markers. That means these markers, this figure is from OpenSim software, and this is the experimental markers. These markers are placed in the gate laboratory for the measurement of different length parameters in the musculoskeletal model. And this measurement data is used for scaling. The dimensions of each segment in the model are scaled so that the distances between the virtual markers match the distances between the experimental markers. Okay, this was the first step in which we do the scaling. And the next step is inverse kinematics, in which we use the kinematic data, which is measured in a gate lab, to estimate the joint kinematics, which are the joint angles. So the inverse kinematics tool steps through each time frame of experimental data and positions the model in a pose that best matches experimental marker and coordinate data for the time step. So this is the inverse kinematics tool which we can use in the OpenSim software, and the inputs for this inverse kinematics is this subject 01 WAC1.trc, which is the measured data from the gate laboratory. And this is the OSIM, means the OpenSim model, the musculoskeletal model. And this one input file is an XML file in which we input different settings parameters for performing this inverse kinematics. And the output is this MOT file, from which we get the joint kinematic parameters, which are the joint angles. Okay, after knowing the joint angles and the joint kinematics, we do the inverse dynamics. So in the inverse dynamics, so we estimate the joint moments, joint reaction moments, and joint forces. The inverse dynamics tool determines the generalized forces at its joint responsible for a given movement. And this the inverse dynamics tool solves the equations of motion F equal to ma in the inverse dynamic sense, will the net forces and torques at each joint which produce the movement. So here we can see this is the inverse dynamic steps. Input for inverse dynamic steps is this MOT data, which is the output from inverse kinematics, and the ground reaction force data, and the musculoskeletal model, and one XML file to specify the different settings parameters. And output is this inverse dynamics force file, from which we know the joint forces and joint moment, joint torques. Next is the static optimization, using which we can estimate the muscle forces for the musculoskeletal model at its instant of time. So static optimization resolves the net joint moments into individual muscle forces at its instant on time. And in the static optimization tool, these are the inputs, which are this WAC1 underscore IK. So this was the output from the inverse kinematics. Then we input the ground reaction force data, and we input the musculoskeletal model and one XML file to set up the different settings parameters. And these are the outputs from which we know the muscle activation, muscle force, and muscle controls. The muscle forces are resolved by minimizing the sum of squared muscle activations So this is the equation which is used for the minimization. This is the summation of this summation of the square root of muscle activations. A is the muscle activation. And this optimization equation is minimized with one of the following constraints. Here, the first equation represents the muscles as ideal force generators. And the second equation represents muscles using these force length velocity properties. So now I will give you this demonstration using the OpenSim software, uh, how to perform this inverse dynamics, inverse kinematics, and the static optimization. I will show you. First, I will share the screen. I hope my screen is visible. So it is visible. So here we will open the OpenSim software. So this is the graphical user interface or GUI of the OpenSim software. So here first I will import one musculoskeletal model, which is the full body musculoskeletal model. So this is the musculoskeletal model. As you can see, this musculoskeletal model consists of these rigid bodies, which are the bones. Then there is joint, knee joint, hip joint, ankle joint, all the joints, and the actuators, which are the muscles. If we expand this model, we can see these bodies, which are the rigid bodies, which are different bones, pelvis, femur, tibia, talus. Next, there is joints. We can see hip joint, knee joint, ankle joint, subtalar joint, hip joint, joints. Then in the forces, there is muscles. All the muscles are here. So first step was scaling. So first we will do the scale model. So here for doing the scaling, we need to load one XML file to specify the different scaling parameters. Here this subject01 underscore setup underscore scale is import. Here you can see this generic model data. It has a mass of 75 kg. But after scaling, we'll get the mass of the subject as 72.6 kg. And there are some scale factors. We'll do a scaling. Okay, so scaling is done. You can see this model is generated after doing the scaling. Also, we have got the markers. Markers are placed in some bony landmarks. So next, we have to do the inverse kinematics. We'll do inverse kinematics. Again, we need to load one XML file to load the different settings parameters. So we'll load this setup underscore IK. Then so we'll run this. So you can see now this musculoskeletal model means this data for inverse kinematics was recorded for a walking activity. So this person is walking. So after doing the inverse kinematics, Now we got the inverse kinematics results. Now we can plot different joint kinematic parameters, joint angles. You can plot, let me show you. You can plot this pelvis rotation, hip flexion rotation, hip abduction rotation. Okay, hip flexion. This is for right hip joint. We'll select for the left hip joint, hip flexion L. Okay, then X quantity, we need to select time. Okay. And so you can see this red color. This is the hip flexion rotation, hip flexion angle with respect to time for the right hip joint, and this the blue colored one is the hip flexion angle for with respect to time for the left hip joint. So likewise, we can plot different hip angles, means different joint angles with respect to time for this gait cycle. Next is inverse dynamics. So now we'll do the inverse dynamics. So we have loaded the motion, which means the kinematics, joint kinematics results from after doing the inverse kinematics. And we'll filter the coordinates to reduce the noise, and we'll load the external load file here. External load means the ground reaction force, which is acting, which acts when we walk on the ground. So I will import that file. That is this subject 01 walk1 underscore ZRF. This is the file, ML file. So I will run this. Done. Okay, so now we can plot the joint moments. We can plot Y quantity, ID results. First, we need to load that file, load file, inverse dynamics.sto. This file was generated after doing the inverse dynamics. This is the output of inverse dynamics. So we'll load this. So you can see different joint moments we can plot. So hip flexion moment and hip flexion moment for the left hip joint. I will plot these two moments. That's one at a time. Okay. So you can see this is blue colored one is the hip flexion moment for the left hip joint, and the red colored one is the hip flexion moment for the right hip joint with respect to time for this walking activity. Okay, so this was the inverse dynamics from which we get to know the joint moments for different activities. Next, we will do static optimization, from which we will know the muscle forces or muscle activations during this particular walking activity. So we'll do the static optimization. In this, we need to load the motion from inverse kinematics results. Again, we need to filter the coordinates. And here we can see that in the static optimization, we do the minimization of the in the static optimization, we minimize this equation, sum of the square of muscle activation. So in the software also, you can see sum of muscle activation square. This is the objective function which we minimize. And we use the muscle force length velocity relation constraint. And here we need to add the external loads, which is the ground reaction force file. And we need to apply one actuators also, because if we don't use the actuators, then static optimization will not be successful. Static optimization will fail. So we need to add the actuators, MC actuators. Okay. And the static optimization. So you can see this optimization is running in the background. This is the status of this running. Status of the static optimization. So static optimization got completed, and now we can run this again. You can see while running it, while walking, you can see there is change in the muscle colors. Sometimes it becomes blue, sometimes it becomes red. So blue means the muscle is less activated, or and when these colors getting changed from blue to red, it means the muscle is getting more activated. Means its activation is getting changed between 0 and 1. 1 means fully activated and 0 means no activation at all. So in between blue and red means the muscle activation is in between 0 and 1. So now we can plot the muscle activations and plot the y quantity to load the file. Static optimization activation. Here we can plot the muscle activation for different muscles. These are the muscle names. So I will plot it for gluteus medius, left and right. Gluteus medius on left. Gluteus medius on right. Okay. The next quantity will plot time. Okay. And so you can see this is the plot for muscle activations for the walking activity. So here we can see at this time the muscle is fully activated. The muscle activation is 1, and at the in this between time 0.8 to 1.3, the muscle activation is 0 or very less. So blue colored one is for the left muscle, and the right colored one is for the right muscle. Red colored one is for the right muscle. So so these are the muscle activations for this timings for these two muscles for this activity. Similarly, we can plot the muscle forces, plot the static optimization force storage file, which stores the muscle forces for this particular activity. So we will plot gluteus medius R and gluteus medius L force, muscle force. Okay, X quantity time. And so here you can see this force. A maximum force of 650 Newton, around 650 Newton, and minimum force is around 8 Newton, something like that. So likewise, using this OpenSim software, we can estimate different muscle forces and different joint moments uh, and joint angles for different activity. Yeah, so this was all about today. Okay, so there will be one more class, which will be a revision class on 14th of October, Tuesday, from 6 to 8 p.m. You can join this class using the same link. This class I will again revise all those concepts from this course, starting from week 1 to the last week. Yeah. So